What we're going to do today is we're going to talk about these three theorems, the side-splitting theorem, the two-transversal proportionality theorem, and the triangle angle bisector theorem. And we're going to use those theorems to find missing lengths of sides and segments, okay? And unfortunately, they're not definitely not postulates. They're not duh. You have to stop and think about it. So we'll go over them one at a time and try to help you figure out a way to remember them. But you really basically have to just memorize them. So add these to your flashcard list and practice them. All right. So the side-splitting theorem says if a line that's parallel to a side cuts through the other two sides or splits the other two sides into two pieces, those two pieces are in the same proportion. Okay? So the most famous one, the one we just used, right, is the mid-segment theorem. That has the same proportion, isn't it, 1 to 1? Right? Like if this is 5, this would be 5. If this is 4, this would be 4 because it's a midpoint. But you can have parallel lines anywhere. You can draw a parallel line like that. You could draw a parallel line like that. I mean, any parallel line to the side is going to divide the other remaining two sides, going to split them proportionally. So like if this is, let's just have one here. So like if, for instance, if this red line were parallel to this one, it could split this into 1 and 5, and maybe this one was 2 and 10. They would have the same proportion, same ratio. So any parallel line is going to split the other two sides proportionally. Okay? That's the side-splitting theorem, because it splits the sides. The two transversal proportionality theorem, which kind of goes with this one, but I like the two transversals in the name because it helps you remember what it's talking about. So the two transversal proportionality theorem says if you've got 3 or more parallel lines that are intersected by 2 different transversals, okay, then they divide those transversals into equal pieces, or into proportional pieces, not equal, proportional. Okay? It's sort of, this one is the what's it called, the slap chop theorem. Have you ever seen that commercial where it's like a machine that you put a potato in and you run it through the machine and it slices the potato like nice and evenly? Like a mandolin? Yeah, like a mandolin slicer, right? With a little less worry about your hands. Yeah. Okay, that's what this is saying. Like, if you put the potato straight down in, it's going to cut even fries. If you put the potato in sideways, it's still going to cut the same thickness, right? They're all going to be the same proportion. They just may look a little different, but they're going to be in the same proportion. So, like if this is 2 to 3, if this chopped off 3 inches here and 2 inches there, and on this one it might chop off 3 inches and 4.5 inches. Okay, they'll be in the same proportion. Okay, and the third one is the triangle angle bisector theorem. Okay, we've bisected angles now for what, 3 chapters? It doesn't say anything about where it crosses the base. When we draw an angle bisector, the only thing we know for sure is that it splits this angle into 2 equal pieces. Well, now, if I draw an angle bisector, I can say, if I had this triangle and this side was 8 and this is 6, okay, and this side was 8 altogether, let's see, 7, Okay? The triangle angle bisector theorem says that this angle bisector splits the side that it intersects in the same proportion as these sides. So if this whole length is 7, then these must be split into 4 and 3 because those would have the same proportion as those. Does that make sense? Yeah? Okay, so those are my 3 theorems: side splitting, 2 transversal proportionality, and triangle angle bisector. Okay? And going back to side splitting for a second, the converse of the side splitting theorem is also true. So if we've got the 2 sides of a triangle that are split proportionally, then we can say that these 2 lines are parallel. Because remember, up till now, every time we want to say 2 lines are parallel, what's the first word you always have to say? Converse. Converse of, right? Converse of alternate interior angles. Converse of same side interior angles. Converse. Same thing here. If I want to prove that these 2 lines are parallel, I'm going to use the converse of the side splitting theorem. Okay? All right. So let's, I'm not sure why I have this double, but let's say I've got this picture and I want to prove or verify that MN is parallel to KL. If they are parallel, what has to be true? Michael? Not the triangles, but the sides. Remember, because we're using the side splitting theorem. So if we want to prove that these 2 are parallel, we want to prove that it's splitting the side proportionally. So in order to prove that MN is parallel to LK, I'm going to prove that the ratio of side LJ, which is 15 to 30, is the same as the ratio of KJ, which is 21 to 42. Okay? To check that, I just reduce it. Both of these are divisible by 15, right? So that's 1/2. Both of these are divisible by 21, so that's 1/2. So is MN parallel to KL? Yes, because of not side splitting, converse of side splitting. Okay? So far so good? Questions? Comments? Concerns? Okay. All right. Which theorem are we using here? We got 3 parallel lines. Right. The 2 transversal proportionality. Okay? So take a minute and see if you can fill in all the missing pieces here. Okay. So basically this is saying that each piece is in proportion. So AB is to BD the same way that AC is to CE. Okay, so this one here uses the triangle angle bisector theorem, which says that the angle bisector divides us into the same proportion as their corresponding sides. So that means x minus 2 and x plus 1 will be in the same proportion as the other 2 sides, 12 and 16. All right, and then I cross multiply and I get 16x minus 32 equals 12x plus 12. I'm going to subtract 12x and add 32, so that gives me 4x equals 44, so x is 11. Here's the side splitting theorem, which says that this parallel parallel line to this one splits, we can tell they're parallel because they have these two marks. It splits the sides into proportional pieces. So 6 to 4 is the same ratio as 8 to whatever KL is. So I cross multiply, I get 6x is 32. So x is 5 1/3. All right. And again, the triangle angle bisector theorem says that 8 and y minus 2 have the same proportion as 4.5 and y over 2. So I have 8 over y minus 2, and that should be equal to 4.5 over y over 2. Okay? Cross multiply, and I get y over 2 times 8 is 4y. And 4.5 times y minus 2 is 4.5y minus 9. I'm going to add 9 to both sides, subtract 4, and I get 9 is equal to 0.5y, so y is 18. All right? And then this one, for these to be parallel, it has to split the side proportionally. So if this whole thing is 27 and this is 15, this would be 12, because 12 plus 15 is 27. If this is 20 and the whole thing is 36, then this would be 16. And then I just have to check that the ratios are the same. So 12 to 15 should be equal to 16 to 20. Reduce these, like they're both divisible by 3. So I get 4 over 5 on the left. And on the right, both divisible by 4, I get 4 over 5 again. So I can say that DE is parallel to AB by the converse of the side splitting theorem.